Hi, this is Professor Fernandez. In this example, in this video, we'll work on example 4.12 from Calculus to Simplified. So this is an example that is going to get us working with geometric series and figuring out, determine which of these geometric series converge. In example, in part D here, x is some fixed number. So think of x as like 7, negative 12, some number that we just don't know but doesn't change, not a variable. For those that do, for this geometric series that do converge, we're asked to find their sum. Okay, now we have some sense of what we're doing. So first, convergence. Remember that a geometric series converges, right, if certain properties hold, specifically about the R value. So let's first review geometric series first. Geometric series looks like this. So it's a series where there's a starting term, and then every other term in the series is that starting term multiplied by some number r, right? So a times r gives us ar, and then multiply times r again. So ar times r is ar squared, gives us that second term. And then we keep going like that. So every term is just multiplied by r. That makes it a geometric series. This is theorem 4.9 in the book. It tells us that these, geometric series converges, first of all, if the absolute value of r is less than 1. That means that the r value has to be between -1 and 1. If r is 7, diverges. If r is 1/2, converges, right? That's a quick example. Second thing, also if r equals 1, right, also diverges. So that's all part of what's here. Second thing, once we know it converges, what does it converge to? So I'm looking down here, converges to a over 1 minus r. So this is the benefit of figuring out what the first term in a geometric series is. That will be your a value. And then figuring out what this r factor is, right? That would be your r value. Once you know a and r, the series, if it converges, will converge to a over 1 minus r. Okay, so that's a quick little review of the theorem. So now let's apply that over here. Part of applying this theorem and just working with geometric series is figuring out whether it is in fact a geometric series. This problem statement tells us that, but let's just talk about it. So over here, one way you can do this is you can start writing out the terms of the series. So this series starts at 0. So if I put a 0 there, I get that term. And then the next one is n equals 1. The next one is n equals 2. And I keep going. So 4 to the 0 is 1. So this term is just 5. And then this is 5/4, and then this is 5 over 4 squared, so on and so forth. You can see that in this series, right, this is the a term. That's the first term in the series. And then the next one I can write as 5 multiplied by 1/4. So, that is the r value, right? That's what I multiplied a by to get ar, the second term. I can confirm my suspicion that r is 1/4 by looking at this third term. So this is 5 times 1 over 4 squared, which is 5 times 1/4 squared. So this is a, and this was r. So this entire term is ar squared. So I think I've got it. I think this is the series a plus ar squared. And it seems to keep going with that pattern. So indeed, geometric series. Okay, I won't review that for the rest of these, but I did want to just confirm and review that before we go off and determine whether it converges and find its sum. Okay, so for this series, we have identified a, right? So a is 5. There it is. We also identified r. So r is 1/4. Does the series converge? Well, question, is the absolute value of r less than 1? 1/4 in absolute value is just 1/4. It's already positive. And indeed, 1/4 is smaller than 1. Check. So yes, the series converges. And then we're asked to say, to find the sum of the series. What does it converge to? Okay, well, we've got our a value. We've got our r value. So what does it converge to? Erasing all this mess here, like we said earlier, converges to a over 1 minus r. So I have my a is 5. I have my r is 1/4. So that's what it converges to. And if we wanted to simplify this, right, that's 5 divided by 4 over 4 minus 1 over 4, which gives us 3 over 4. 5 divided by 3/4 is 5 times 4/3. So that's 20 over 3. So that is the sum of this first geometric series. Okay, so I'm going to erase all this stuff and then redo the analysis here. Make things a little easier for me to erase. Bigger eraser. Redo the analysis for the second part. Okay, so I'll take for granted that this is a geometric series, but still, good to write out its terms because we need to find the a and the r value. So if n equals 0, this is 5/4 to the 0. Then we get 5/4 to the first, and we get 5/4 squared, and then so on and so forth. 5/4 to the 0, that's 1. 5/4 to the first, that's just 5/4. And then I can see more directly here what's going on. This is my first value, that's a. And then this should be AR. A is 1, so that means that 5/4 itself has to be the R value, right? Because if A is 1, I get 1 times 5/4 gives me my 5/4. And then again, to confirm here, this should be AR squared. A is 1, R is 5/4. So AR squared should be 1 times 5/4 squared. Indeed, that's the term. So again, geometric series, I confirmed my A value, I confirmed my R value. Does it converge? Well, same question from before. Is absolute value of R less than 1? In this case, R is 5/4. The absolute value is 5/4. That is not less than 1. No. Right? 5/4 is 1 1/4, 1.25. So actually, it's bigger than 1. So this series over here does not converge. It diverges. And so we're not going to find its sum. If a series diverges, right, doesn't have a sum. Okay, so I'm going to move on to this next one. Same deal, we'll speed things up a little bit here. The n equals 0 term is this one. The n equals 1 term is this one, and so on and so forth. Minus 4/5 to the 0, that's 1. And then over here I have plus minus 4/5. And then one more term would have been minus 4/5 squared. This is my a value. This is a times r. A is 1, so r is minus 4/5. And then this indeed is AR squared. So I've got my A value, I've got my R value. Does it converge? Is absolute value of R less than 1? Well, R is minus 4/5. Take the absolute value, I get 4/5. And that is indeed less than 1. So yes, this series converges. And what does it converge to? Well, I found my A value. A is 1. So A over 1 minus R. And R is minus 4/5. So that's what it converges to. And then I can simplify this thing just like I did before. If I do that, you can verify that you would get 5/9. So the series converges to 5/9. Okay, last example to work on here. What if I look at this last geometric series, which looks a little weird? It doesn't have numbers in it, right? So the n equals 0 term here is x to the 0. And then n equals 1, and then n equals 2, so on and so forth. So this is x to the 0, 1 plus x squared, and it keeps going. So, maybe there is one number, but the rest of it has x's in it. Again, don't think of x as a variable. We were told early on that x is a fixed number. So think of x as a number. You just, can't see it or it hasn't been chosen yet, but it's a number. Okay, so this is my a value. This has to be a times r. A is 1, so r has to be x, right? That's right. 1 times x is x, which is this term. And then this has to be a times r squared. A again is 1, and r is x. And indeed, it gives us x squared. So I got my a value, I got my r value, and then question, does it converge? Well, is the absolute value of r less than 1? R is x. So here I run into something that is not so easy to verify. So my conclusion is that the series, this one up here, is going to converge only when the absolute value of x is less than 1. We were told x is a fixed number. So for example, if x were 7, this is not true, right? 7 is not less than 1 in absolute value. If x were, I don't know, negative 1/2, then the absolute value of that is 1/2, which is less than 1. right? So that one would converge. So depending on what x is, specifically if x is, less than 1 in absolute value, then we get convergence. And actually, this series will come up later. It comes up later in the book. Maybe it will come up later in your course when you start talking about power series. So now we have this result that tells us when this geometric series converges. And what does it converge to, assuming, again, that absolute value of x is less than 1? Well, it converges to a over 1 minus r, as the geometric series always do, right? That's the theorem down here. And I found my a value. Looks like it should be an a here. A is 1, and r is x. So there we go. So the conclusion, which is really cool to highlight, is that this geometric series converges, sums to a over 1 minus r, so long as the geometric series actually converges, right? Which we said happens when absolute value of x is less than 1. Again, you will see this result in at least 2 more ways in your course and in this book. Number 1, you'll later understand it as a power series. And number 2, you'll, even after that, later understand it as a Maclaurin series, which is a specific type of Taylor series. All right, so you saw it here first in this video, right, and in this section in the book. Remember that in this case, by a clever choice of choosing x as a fixed number, we can see this sum in a third way as a geometric series. So this one example unifies and gives you 3 different perspectives: the geometric series, a power series, and Maclaurin series. That'll come later on this one series. Okay, see you next time.